In this lab, we will track the motion of a falling object over position over time as it is dropped from rest at a height. In order to do so, we will create various computational models that incorporate the forces of gravity and drag, and we will then assess the accuracy of those forces upon the models with respect to the observed model. And these models incorporating gravity and drag were found to have been the most accurate to the observed motion, rather than a model that only incorporated gravity or could have only included one force. The fundamental forces and principles we will be observing over the course of this lab will be the forces of gravity and drag. Gravity is a force that is delivered in the negative y vector, and it is situated on Earth's system over its surroundings, and it pulls objects that are midair back to its surface. And the constant for acceleration of gravity is 9.8 meters per second squared. Note the units and the fact that we do not have a direction with this constant. And so in the gravity formula, we will use a j-hat direction vector. For drag, a similar formula is necessary. We will use a v-hat to signal the direction in the y vector, and we will also use the magnitude. And the b is a proportionality constant which we will solve for in the duration of our model. Drag is a force that acts in the opposite direction of an object's travel. And so the atmospheric conditions will bring an object to work backwards, and so it won't travel in the forward direction. And Newton's second law, similarly to what we did in the first lab, we'll use the momentum principle in order to derive the formulas of position update and velocity update to look at force over time and how it affects the velocity and position over time. The software we used was Tracker. Tracker is a program that allows you to look at the position over time and track its movement. And so we were able, for the observed model, to find the position of the object as it went down, the y vector. And instead of using the x-axis, we used a y-axis and looked at its negative direction over time. In the tracker model, we have both the gravity and drag model. For just the gravity model, we will only include weight, which is the negative of the mass times the gravity constant times j-hat, and that will be our only net force. And then we will plug that into the Newton's second law position and velocity updates in order to get a graphic. And for the gravity and drag model, it will be a similar procedure where we have the drag and the weight, and the net force will be weight and drag. And then for the proportionality constant, there's no specific way for us to know what the proportionality constant is, as we don't know exactly what is happening in our surroundings. We haven't tested for that, and so we use plug and chuck in order to see what will be the most similar to our other graphs. And so for the graphs, we have the drag and gravity model is blue, just gravity would be the salmon color, and yellow is the observed model. And we can see the drag and gravity model and the observed model have the most closely correlated trajectory, whereas the just gravity has a much steeper drop, and it does not factor in the backward force that drag implements onto the system. What does this mean? Well, according to the graph, the drag and gravity model was not entirely accurate because it was not completely going downward at the same rate as the observed model. And so looking at that, we can assume that that might be a problem with the proportionality constant. Since it is a plug and check method, it is a little bit inaccurate, and so we might need to measure that. But in all, the more accurate model was the drag and force model, drag and gravity model, and that is the most informative of what our real system and what its real surroundings looks like, because we need to sum up all the forces in order to know what the net force is that creates this velocity and position. If an object was initially thrown from rest rather than dropped, then there is a greater initial velocity, and so there will be an acceleration that is not gravity acting upon the ball. But that also means that the drag that is acting against the ball will also cause it to slow down until the net force ultimately is zero. And so we will have a terminal velocity that is still the same between both of them, just as long as the drag is also the same. And so the net force has to balance out and maintain equilibrium once the acceleration from the initial throw has been resolved from the drag.